This divider slide marks the transition from logging environment to the third major section, types of logs. At this stage, it is helpful to remind students that now that we understand the measurement environment, we can begin discussing the individual log types and what they tell us. The central idea from here onward is that each log measures a different physical property, and therefore each provides a different piece of the reservoir puzzle. The power of well logging comes not from a single curve, but from integrating multiple logs together. This slide introduces lithology logs, whose purpose is to identify rock type. Since most hydrocarbon accumulations are found in sedimentary rocks, especially clastics and carbonates, lithology logs are essential for formation evaluation. The slide highlights three important lithology-oriented logs: gamma ray, spontaneous potential, and photoelectric effect. Before we estimate porosity, saturation, or reserves, we first need to understand what kind of rock is present. A clean sandstone behaves differently from a shaly sand, a limestone, or a dolomite. So lithology logs are the foundation of formation identification. The gamma-ray log is one of the most common and important lithology logs. It detects natural gamma-ray emissions from radioactive isotopes in the formation. High gamma-ray readings usually indicate shale, because shale commonly contains more radioactive elements associated with clay minerals. Clean sands and many carbonates usually have lower gamma-ray responses. This makes the gamma-ray log extremely valuable for distinguishing shale from cleaner reservoir intervals. It is also useful for identifying gross reservoir zones, correlating stratigraphy between wells, and defining net to gross. The slide says the depth of investigation is about 1.5 feet, which means it mainly samples a shallow radial zone near the borehole. When teaching this slide, stress the practical rule: high gamma ray suggests shale, low gamma ray suggests clean formation, but also remind students that uranium-rich or radioactive sands may sometimes complicate that rule. The spontaneous potential, or SP log, is one of the oldest logging methods. It measures the natural direct current voltage difference between a surface electrode and an electrode moving along the formation in the wellbore. This electrical potential develops because of electrochemical differences between drilling mud and formation water, especially when a permeable bed allows ion exchange. SP is very useful for identifying permeable formations such as clean sandstone. Shales tend to define a baseline, while clean permeable sands often show a deflection away from that baseline. So SP is not just a lithology log, it is also a permeability indicator. It can help identify reservoir intervals and, in some cases, support qualitative estimates of shale content. This slide gives a worked SP example. The shale baseline is plus 40 MV, the sand baseline is minus 80 MV, and a formation interval reads minus 30 MV. By comparing where the measured SP lies between the shale and clean sand references, the shale content is estimated as about 0.42. This is an excellent teaching example because it shows that logs are not only qualitative pictures. They can also be used quantitatively. The SP curve becomes a basis for estimating shale content or relative cleanliness of a formation. However, remind students that SP interpretation depends on mud and formation water chemistry, so it is not a universal standalone tool. It works best as part of an integrated log suite. The photoelectric effect log, often called the PE log, gives another perspective on lithology. It is based on the absorption of low-energy gamma rays by inner orbital electrons in the formation. Because this absorption depends on atomic number, different minerals show different PE responses. This is why PE is especially useful for differentiating lithologies such as sandstone, dolomite, limestone, shale, or salt. Hydrocarbons in water have low atomic numbers and contribute very little to PE response, so the measurement is dominated mainly by the rock matrix rather than the fluid. That makes PE a good lithology discriminator, especially when combined with density and neutron logs. This slide elaborates on the PE concept by showing typical values: sandstone around 2, dolomite about 3, shale roughly 3.5, salt around 4.5, and limestone or anhydrite around 5 barns per electron. These are useful benchmark values for students. This is also a great slide to emphasize integration. If gamma ray suggests a clean formation, density neutron responses suggest porosity, and PE helps distinguish whether the clean formation is sandstone, dolomite, or limestone, then the interpretation becomes much stronger. This is why log reading is sometimes compared to reading music. A single note matters, but the full pattern gives the meaning. Now the deck moves into porosity logs, which include density logs, acoustic or sonic logs, and neutron logs. These are among the most important formation evaluation tools because porosity is one of the key reservoir properties controlling storage capacity. Each of these logs estimates porosity from a different physical principle. The density log measures electron density-related bulk density. The sonic log measures acoustic travel time, which depends on the rock frame and pore volume. The neutron log responds mainly to hydrogen content, which usually correlates with fluid-filled porosity. By comparing these logs together, we get a stronger estimate of porosity and sometimes additional clues about lithology and fluid type. The density log uses intermediate energy gamma rays from a radioactive source in the tool. These gamma rays undergo Compton scattering when they collide with electrons in the formation. The measured count rate depends on the electron density of the formation, which is closely related to bulk density. Once bulk density is measured, we can combine it with the matrix density of the rock and the density of the formation fluid to estimate porosity. This is a very practical calculation, And the slide includes an exercise using specific values for bulk density, matrix density, and fluid density. This is one of the most commonly used porosity estimation methods in petrophysics, especially in clean formations where matrix density is reasonably well known. This exercise is a great practice. The formation bulk density is 2.30 g/cc, matrix density is 2.62 g/cc, and fluid density is 0.869 g/cc. The goal is to calculate porosity. The logic of the calculation is that if the bulk density is significantly lower than the matrix density, then the formation must contain a meaningful amount of lower density pore fluid, implying porosity. This type of exercise helps students move from concept to application. It also reinforces an important principle: density logs do not measure porosity directly, they measure bulk density, from which porosity is inferred.